I remember the days when I was in high school, sitting in maths class learning how to graph parabolas like y equals x squared. Back then, the idea that you could even have graphs that were not straight lines blew my mind. But one thing I really liked about graphing equations was how you could rotate a curve 90 degrees just by swapping the y's and x's around, and how changing the signs of the x's from positive to negative would rotate the curve 180 degrees. This is power, I thought. Of course, it wasn't until much later that I realized it's not actually true. An easy counterexample is the line y equals x. When you swap the y and x around, well, nothing happens. And making the x negative is in fact what rotates at 90 degrees. Mini-me wasn't able to comprehend back then that it only works if your curve has a nice line of symmetry that goes straight vertically up, parallel to the y-axis, such as in the case of y equals x squared. After mastering the art of rotating the parabola through multiples of 90 degrees, the next question to pose is how do you rotate a parabola 45 degrees? And once you've done that, how do you rotate it 60 degrees, and 30 degrees, and 52.613 degrees? The thought lingered like a splinter in my mind. I asked the teacher, but she said she didn't know. It wasn't something we learnt at school. So I went home and forgot about it. Life goes on. I've come a long way since then. Recently I've been learning about linear algebra, vectors, matrices, and in particular, linear transformations. Linear transformations are wicked. They're when you take any plane with some kind of coordinate system and transform it in such a way that you can rotate and stretch the x and y axes themselves, forming an entirely new kind of plane. The actual maths behind it all is very beautiful but not so easy. I certainly would not have understood any of it all those years ago. So instead of going into the language of linear algebra, I thought I'd try and show you how to rotate a curve using the knowledge I had in high school. To start off, let's consider the special case of our favorite parabola, y equals x squared. In order to make things slightly easier, we're going to convert the equation y equals x squared into its parametric form. If you haven't heard of parametric form before, don't worry, it's really simple. All you do is introduce a new variable like x and y, usually called t, and you express x and y in terms of that single variable t. For example, y equals x squared, so if I let x equal t, then y must be equal to t squared. Therefore, the parametric form of y equals x squared is x equals t and y equals t squared. Hopefully you can see that both things are saying the same thing, but you may also be wondering what the point of doing this is, since we're just making things more complicated by adding in this t for seemingly nothing. The point of it is, now we can represent any point on our parabola in terms of only the variable t. For example, if we want to label a point on the parabola, we could label it x and y. But that doesn't tell you much, since x and y could be anything. But since the point lies on the parabola, we know x equals t and y equals t squared. So a better pair of coordinates for this point would be t and t squared. This way, we algebraically encode the information that this point lies on the parabola y equals x squared. Okay, the way to go about rotating the parabola is actually not by rotating only the parabola, but the entire xy plane itself. So let's draw on top of this plane the same plane, just rotated by some angle, which I'll call theta, along with the rotated parabola. As you can see, the point t has moved to a new location. In the rotated green plane, it will still have the coordinates t and t squared. But the real question is, what are its coordinates in the original red plane? Since the point t has coordinates t and t squared, we can construct a rectangle from the origin to the point t, and it will have sides of length t and t squared in the red plane. The good thing about this is that the distances are the same in the green plane. We can draw the exact same rectangle with side lengths t and t squared in the green plane. Our diagram's getting a bit messy here, so let's draw it out separately. Right, so now what? Time for some trigonometry. Let's construct right-angled triangles out of the two sides of the rectangle, t and t squared, such that the sides of the triangles are parallel to the x and y axes in the red plane. One thing to note though is that this angle is in fact theta. Why is that? Well, because this angle is 90 minus theta, since it has to add up with theta to make this right angle of 90 degrees. Then this angle had better be theta, since the sum of the angles in a triangle is 180 degrees. And because we have two parallel lines, with another going through them, that means the opposite angles are equal, so this angle is indeed theta. Anyway, we have two right-angled triangles, one involving t, one involving t squared, and both involving theta. We can find the lengths of their other sides using trigonometry. Let's label the single t triangle's sides A and B. Cosine is adjacent over hypotenuse, so cos theta equals A on t, or in other words, A equals t cos theta. Likewise, sine is opposite over hypotenuse, so sine theta equals B on t. B equals t sine theta. Doing the exact same thing with a t squared triangle gives you t squared sine theta and t squared cos theta. Okay, so we found the lengths of the triangle's sides. Let's put them back in our picture and see what we've got. Nice. What were we trying to do again? Oh yeah, we were trying to find the coordinates of this point T in the red plane. Oh well, that's easy now. Its y coordinate is how far up it is on the y-axis. So it's going to be the sum of the sides going up. That is t sine theta plus t squared cosine theta. The x-coordinate is how far along the x-axis it is, which is the bottom length minus the top length, t cosine theta minus t squared sine theta. Awesome! We have found the coordinates of t. X equals t cos theta minus t squared sine theta, and y equals t sine theta plus t squared cos theta. This here is the parametric form of our rotated parabola, but we want to turn it into a familiar equation with just x's and y's, so we need to get rid of the t's. To do that, we need to combine these two simultaneous equations into one, and eliminate the t variable. We could do that by making t the subject of the first equation, and substituting that back into the second equation, except you'd have to use the quadratic formula, have square roots everywhere, and make everything ugly. Instead, we're going to do something else which is much more elegant. First, multiply the first equation by cos theta. Then, multiply the second equation by sine theta. Next, and here comes the nice part, add the two equations together. The t squared sine theta cosine thetas cancel out, and you're left with t times sine theta squared plus cosine theta squared equals x cos theta plus y sine theta. But sine squared plus cosine squared always equals 1. So that goes away, and all that's left is t equals x cos theta plus y sine theta. Not bad at all. And now you can replace the t's in the second equation with x cos theta plus y sine thetas, which gives you this. The equation of a parabola rotated by any angle, without a single square root. Want to know what the equation of y equals x squared rotated 45 degrees looks like? Just plug in theta equals 45 degrees. What about 60 degrees clockwise? No problem, do the same thing with negative 60 degrees. It'll work for any angle. If you managed to understand all of that, I salute you. But the title of this video is how to rotate any curve by any angle, not just parabolas. Now we're going to do the entire process again, but with an arbitrary curve y equals f of x. Have no fear, it's almost identical as the case of the parabola. First, convert to parametric form. Y equals f of x, so if x equals t, then y equals f of t. That means every point on our curve has coordinates t, f of t, where t is a variable that can be anything. We also need a rectangle, which comes from the fact that since t is labelled t, f of t, you can draw a rectangle from the origin with side lengths t and f of t. Next, we rotate not just the curve, but the entire xy plane itself by some angle theta degrees. Everything, including the curve, the rectangle, and the point t, gets rotated about the origin. And again, the question is, what is the coordinates of the rotated point P with respect to the red plane? We have our rectangle with side lengths t and f of t rotated by an angle of theta degrees. Then, draw up right-angled triangles using these lengths. Note that, for the same reasons as before, this angle here is also theta. And using the same tricks of trigonometry, this side will be t cos theta, since it's adjacent to the angle theta and the triangle's hypotenuse is t, while this side will be t sine theta, since it's the same but opposite the angle theta. In the second triangle, its hypotenuse is f of t, so the top side will be f of t times sine theta, because it's opposite the angle theta. And the other side will be f of t times cosine theta, because it's adjacent to the angle. Great, so for the y-coordinate of the point t, that corresponds to how far up along the y-axis it is, which, as you can see from the diagram, is going to be the sum of the heights of the triangles, t sine theta plus f of t cos theta. Likewise, the x-coordinate of the point t corresponds to how far along the x-axis it is, which is going to be the bottom length minus the top length, t cos theta minus f of t sine theta. So for an arbitrary curve y equals f of x, when you rotate it through an angle of theta degrees, its parametric form will be x equals t cos theta minus f of t sine theta, and y equals t sine theta plus f of t cos theta. All we have to do now is combine these two simultaneous equations into one and eliminate the t variable. Déjà vu. We do exactly the same thing as before. Multiply the first equation by sine theta, and the second equation by cos theta. Add the two equations together and watch the magic unfold. The f of t's cancel out, and because sine squared plus cosine squared equals 1, you get the same thing as before. T equals x cos theta plus y sine theta. Put this back into the second equation, and you get this very simple looking thing. We can simplify it a bit though by bringing this y sine theta squared to the other side, and combining it with a y on the other side to make y cos theta squared, since 1 minus sine squared equals cos squared. Everything now has a factor of cos theta, so let's divide both sides by it. Bring the x term over and you actually get a very nice symmetrical formula. Y cos theta minus x sine theta equals f of y sine theta plus x cos theta. Simply amazing. And there you have it. If you want to rotate any curve y equals f of x by any angle theta, all you have to do is plug in the function f and the angle theta into this formula. And there you go. For example, to rotate y equals x cubed by 45 degrees, it would be y cos 45 minus x sine 45 equals y sine 45 plus x cos 45 all cubed. You'd have to expand that cube, of course, which would leave you with y cubed terms and other painful things, but who cares, it works. Still, it's funny that it's only now that I'm able to rotate curves, when I thought of the problem years ago. You're always moving forward when it comes to maths, constantly building from simple concepts to harder ones. But you never look back, you never pause to think about what you once knew, or didn't. It's easy to forget the fact that you do have a past. There was once a time where you couldn't plot a parabola, or you couldn't add. Who knew mathematics could be so nostalgic?